So what we want to calculate is this expectation value. And just slightly have to mention that this omega is the perturbative ground state, and 0 is the free ground state. And the idea is that if E0 represents the free ground state, then the idea that this perturbative ground state is somewhere slightly above this free ground state, and the idea is that this E0 prime with this state of omega can be found based on the ground state, and also the energy is a function of the ground state, let's say. I mean, this is a very stupid notation, but what I'm saying is that all we need is to know the free solutions and then expand it using more and more terms and to be accurate. When I'm not using any index, when I'm saying phi of x and t, that means from now on the free field solution plus some terms that I want to find. And for now, just accept it from me that this free field of x and t, I can write it down with the index I, and this index I is because of the world in interaction or interaction picture, comes from interaction picture. Now what I want to find first, I have to find the ground state. These are two steps. I have to find the ground state in terms of some operation on the free ground state, and also I find phi of x and t as some operation on phi and x and t when there is no interaction. And the other constraint that you can say is that this phi of x and t, if I take lambda to 0, should converge to phi I of x and t. And this is again something that we should have on top of our mind. And let me also draw an axis here. And let me say that I put a time here, I call it t0. You have a choice. You can say t0 is equal to 0, then don't write t0. But I want to write down t0. T0 is when the interaction starts to turn on. And anything before t0 is basically free. And anything after v0, let's say, is not free or interactive. So the point is that when I start from minus infinity, so what we know here is that this part is equal to phi of x and t. And let's say at this point, I'm going to have phi I of x and t0. And what I want to find is that what is my phi of x and t? Simple, it's Heisenberg picture. What does the Heisenberg picture say? The Heisenberg picture say that the evolution of the field is derived by the Hamiltonian. So let's say I want to find the field at point x and t, but that's why I introduced this t0 here based on t minus t0. So what I basically want is that I want phi at point x and t0, and then I evolve it with the total Hamiltonian, and the total Hamiltonian is t minus t0 because the interaction turns on after t0, and then on the other side I'm going to have the conjugate term t minus t0. Okay, we don't have any problem with this term. We already know it's kind of trivial. It's coming from the principles of Heisenberg evolution. The problem is that this h is h0 plus h interaction. And if it was only h0, we know how to deal with it. But since we have this extra term, that's not going to be that straightforward. So phi of x and t is equal to, let's say, phi of x and t 0. And I'm not using any index to show that this is an interactive field. But at the time t0, we know that by the time of t0, the answer is the free solution. And then, I'm trying to create some interacting terms here. So, I want to create some phi of x and t. So this was the evolution. But imagine that now I'm trying to do a mathematical trick. I say exponential of plus IH0, or the free Hamiltonian, of t minus t0. And then you have the exactly opposite term to cancel this one out, t minus t0. And then you have the total Hamiltonian. And the same logic for the other side. So this one is going to be minus IH0 t minus t0, and then plus IH0 t minus t0, and then I have this total Hamiltonian t minus t0. And now I'm gonna absorb this exponentials inside of this, and I call it phi of I and x and t. And I think it's trivial. Why? It's just the definition that we said. We thought that at the point t0, if the field doesn't have any interaction, which means that it only evolves with this free Hamiltonian, then I'm going to have this kind of interactive background field. So now I'm going to have phi of I of x and t, and then the evolution term is exponential of plus I h0 t minus t0 minus h t minus t0. And on this side, I have minus h0 t minus t0, an exponential of plus ih t minus t0. This is equal to phi of x and t. So now it's something interesting here. This Hamiltonian is h0 plus h int, correct? And that part with h0 is cancelled out with this term, and also the similar logic for the left-hand side. So what I'm going to remain with is this. So I have phi of x and t is equal to phi I of x and t, and then I'm going to have exponential. So now I'm going to have minus IH interactive Hamiltonian t minus t0, and then I have I plus IH interactive Hamiltonian t minus t0. And what is the beauty of it is that now we got rid of the background, or h0. If you look at this phrase, there's no h0 here that we have to deal with. So we absorb all the h0. So at the end, we only have to deal with something simple as interactive Hamiltonian. So that's why this one is called phi of I, because phi of I is the phi that it is evolved with the interactive Hamiltonian. That's why this index I goes down here. It's because of that. It's because of this expression, that this component of the field is evolved. It's like only seeing the interactive Hamiltonian. So the dynamic of the field is driven by the interactive Hamiltonian. But this is not our field. This is the interactive field. Our field is the evolution of the interactive field with the interactive Hamiltonian. So I hope the mathematical logic is just simple. We're just doing some arithmetics, and then we saw that we get to this expression like that. And now it's the time to introduce the evolution function. So I can call this Hamiltonian part u of t and t0. And this one, I call it u dagger of t and t0. So my phi of x and t is equal to phi I of x and t, u t t0, and u dagger t t0. Now, what is this u of t t0? So now we're trying to find this u of t minus t0. So let's take a derivative from that, because by taking a derivative, I'm going to write down a differential equation, and then I'm going to solve this differential equation to find ut and t0. How? So I say the I d by dt. So I'm taking a derivative with respect to time of u of t and t0, which means that I'm taking a derivative of this term, exponential of minus I h interactive t minus t0. When I take a derivative with respect to u of t, I'm going to have h interactive times exponential of minus h interactive t minus t0. And now I have the differential equation because this term is u of t and t0. And then I'm going to have the following differential equation. And if I solve this differential equation, I can, you know, find the operator that I want, which is u of t and t0. So how to solve this differential equation? There is a method. Now we want to find the answer to this differential equation for this operator. So the fact that it is an operator doesn't change anything. We still treat u as a function of t0 and t, or I can say t and t0. Doesn't matter. But the point is that how to find it, how to find the generalized solution when we know the value at one point. So what do we know at one point is that if t is equal to t0, then u of t and t0 would be identity. So we know this. So we know this, that this operator in the limit of t goes to t0 is going to be identity. So therefore, I can say u of t0 is equal to identity in the first order, or the zeroth order, sorry, to the zeroth order. And then I have the first order. So the first order, in terms of how to solve this PDE, is minus I, the integral from t0 t dt1 h I of t1. So now is it like that? So what we are saying is that imagine that you have identity operator here, and then now you trying to add something to it. So this is an integral from t to t0 by a continuous act of the Hamiltonian. So if we act the Hamiltonian at each point from t0 to t, we are eventually going to be I plus this term here. That to the first order, this is u of t and t0 in the first order. So this one on top of it is indicating that. And the second term would be minus I squared. So again, the integral from t0 to t, but this one is from t0 to t1, but this one is dt1, this one is dt2, and then I have hi t1, hi t2, and the rest of the terms. Well, the terms have a logic, the same logic. So you might ask again, why does it look like that? First of all, we don't have the general term of h interaction. So in this case, imagine it is lambda over 4 factorial of phi 4. And in this case, imagine maybe we can solve this equation. But in general, we don't have explicit answer of h interaction. So what we are trying to do is to find the generalized answer based on this Hamiltonian, interactive Hamiltonian. But what we did is to basically find the answer of this differential equation by doing perturbative expansion around the first derivative, second derivative. So this action is like Taylor expansion. Maybe I can give you a better visualization. So it's not exactly the same thing, but the logic is the same. So imagine that I have a function x versus f of x. Maybe I say this is y. And imagine I know the value at this point. Imagine this is t0, and I know this is identity. So what I'm trying to do is to go far to t. And so if I want to do it with the first derivative here, let's say, sorry, maybe I draw it better. So imagine this is the first derivative. So the value that the first derivative predicts is so far from the actual value. So you need other terms. So this is like a kind of series that we try to converge it to the real answer. So this is, so now what I'm trying to do is also rephrase this integral in a better way so we can systematically calculate. So imagine I have an integral that the first interval is from t0 to t1, and then t0 to t. And this is dt1, this is dt2, and then I have a Hamiltonian t1 and then a Hamiltonian t2. So I mean, just mathematically, it's like a trick. What is this integral is calculating? This integral is calculating, imagine the area of this triangle. Imagine this is t1 and this is t2. And what we are doing is that, imagine this is t0, t, and imagine this is t0, t. T0 is the same. So what I'm calculating is this. I'm calculating the area of this triangle here. This is equal to this integral here. And instead of doing that, what I can do is to calculate the area of this whole rectangle, and then divide it by 2. So this is equal to 1 over 2. Now I have 2 integral for the calculation of the rectangular area, but now these two have basically fixed boundary. So both of the boundaries are going to be simply from t0 to t, and then I have dt1, dt2, and then what I call it here, time ordered between t1, h1, and t2, which means that when I'm calculating this integral, I always consider which t1 is larger than t2 or t1 is larger than t2. So I'm, basically ordering them in the right way, but at the end, I also have this 1 over 2 factorial. Then I can find also the generalized solution for the n-dimensional case. So I have, imagine t0 to t, and then you have t0 to t1, and then you have t0 to t of n minus 1. And imagine you start with dt1, dt2, and to dtn, and then you have Hamiltonian from t1 to Hamiltonian of tn. This is equal to 1 over n factorial of the integral from t0 to t for dt1 to dtn, but time ordered manner. Because these h, I, they are operators. So imagine I say h, t1, h, t2. Imagine this is different from h, t2, h, t1, just conceptually. So this time ordering is important. So when you're performing the integral, you're spanning all this rectangle, but when you're spanning, you're paying attention which side of this triangle you are. So there is a side when t1 is larger than t2, and there is a side when t2 is larger than t1. So then, now I can rewrite my u operator as identity plus minus I t0 t dt1 h I t1 plus now minus I squared divided by 2 factorial or 2, and from t to t 0, and then I have dt1 dt2 time ordered of hi t1 hi t2, sorry that I'm completely out. And then the third term is going to have the same logic, but if you write down all the terms, you can see just simply it's an exponential term, but this is the exponential term that it is time ordered. So it's basically time ordered exponential of. So now this exponential function, inside of it, there is a operator. So maybe this is all operators. So this is minus I integral from t0 to t, and then I have dt prime. So I'm choosing prime as my variable because now I only have one variable. And this is hi t prime. I mean, I could use t1 instead of t prime, but I want this one to be kind of distinct from this series that I'm expanding here. This t1, t2 was, I was labeling them to say that, these are the number of steps we can take to do this kind of time evolution. But this is basically one continuous final answer. Okay. And if we, but again, this is a kind of integral of a Hamiltonian. This is an integral of an operator. And then you calculate the exponential of that operator. So it's a function of an operator. And then at the end, you time ordered them. So this is what this t is here for. Okay, so probably now we can say we found u of t and t0, which is equal to time ordered of exponential of minus I t to t0 to t of the integral of the interactive Hamiltonian. And that's so beautiful. We can generalize basically the evolution of the field by knowing this operator, but this operator is obtained by doing a kind of infinite series, and now it's up to you to what degree you want to expand this. Okay, in the previous session, we talked about the operator U of t and t0. And this was the operator that we were basically using in order to get the field when we have interactions. So phi of x was equal to phi I of x u dagger u. And again, like we were assuming that this u is a function of two variables, t and t0. And we are assuming that if we have time interval, imagine, the interaction starts at the point t0, and then at the point t, we are at the point that we are arbitrarily having a distance from the interaction. You can always shift this t0, and sometimes you will see that you have to limit this t0 to minus infinity, or I mean, mostly it could be minus infinity, or it can even go to plus infinity. It depends on the context that you want to talk about. But the whole point is that you can always divide the timeline into the two parts. The first part that we don't have any interaction, and basically the fields are free, and then you have when interaction is turned on, and then you don't have any kind of free fields anymore. Now the question is how to get the state omega, or the ground state of the total Hamiltonian. So omega is somehow similar to, again, a free vacuum. So we know about the free vacuum. Omega belongs to the same Hilbert space that the free vacuum belongs to. So they are basically living in the same kind of a space together, but they are not the same entity. They shouldn't be the same entity. So the idea is that if this omega state is a function of some epsilon parameter, and this epsilon parameter refers to the interaction, so imagine h is equal to h0 plus some epsilon interaction, and then you limit this epsilon to 0, you expect the omega goes to the regular vacuum state. But what is their difference really is that they are bases for different kind of Hamiltonian. So again, for reviewing that, we have one space that you would call it Hilbert space of the states. So I mean, the physical state is a coordinate of where the physical system is living in the Hilbert space, and you always depends on what type of Hilbert space that you have for the expressing the state, the physical state. You also have a Hilbert space of operators, or I can say operators on the state, on the states. So there is a kind of interconnection between these two Hilbert space. Hilbert space of the states and Hilbert space of operators. These are Hilbert space, not Hamiltonian. These are just mathematical notation for sets, or the space. Space are like sets. One particular example of the Hilbert space is this kind of spinor Hilbert space. So spinors, they were basically living in a space that there was two parameters here, C1 and C2, and then this C1 and C2 are members of, C2 are members of the complex numbers. Or basically, the state can be infinite dimensional. We previously discussed in the classical quantum mechanics, you have the states that, like x and p, if you have a kind of classical particle pictures, these states are not finite dimensional. They are basically, as you can see, there are infinite numbers of the eigenstates. So for example, if I define operator x, and this operator x acting on x is giving you xx, there is basically, there is infinite number of x, infinite number of locations that could be the eigenvalue of this operator. So the definition of the Hilbert space depends on how many degrees of freedom you have to express your system on. So in the occupation number notation, we basically have this Hilbert space of states And you can always subdivide this Hilbert space into the regions that you can call them the basis to expand the whole space. So imagine that the free Hamiltonian gives you a vacuum, and then you can basically define any number representation, n1 up to p momentum states, and each of them is occupied by n1, n2 up to np, and the whole set of these states are enough to express all of the physical states that belongs to the Hilbert space of the free field. So we're basically talking about the basis of the Hilbert space. And when you have a free field, your basis is systematically constructed from this vacuum. So if you have this vacuum, and then how do you make these states? By using this A dagger K, or this creation and annihilation operators. If you remember, basically this creation operator acts on the vacuum, and it would systematically make you all the states that you need to describe or to expand this whole Hilbert space. And this is called focus space. The focus space is the space that you construct from a certain vacuum, but that vacuum should be the eigenstate or eigenvector of the Hamiltonian operator. So we basically imagine that, again, like systematically, if you have this Hamiltonian operator sometimes in the free field is just H0 operator. And then if you have the state 0, or the vacuum state, acting on H0, and then you sandwich it with another vacuum state, you basically are gonna get E0, because 0, 0, or basically the inner product of two vacuum state is 1. So this is basically how do you define the vacuum. So the vacuum is the base eigenstate of some particular form of Hamiltonian, and then you can construct the bigger space to expand the whole Hilbert space by adding this creation and annihilation operators. So systematically, omega, state omega, is the eigenvalue of total Hamiltonian. So if H is equal to H0 plus H interaction, then H acts on omega. Omega should be equal to E0 prime omega omega. And then again, by defining this normalization, this should be only equal to E0 prime. E0 prime, again, E0 prime should go to E0 when the interaction goes to 0. So omega now is something else, is some other vector. Imagine that these are the vacuum state of the free field and all the members of the focus space that you made out of these vacuum states. And here is another region or another patch of this Hilbert space that it is constructed by the state omega, and then all the other states that belongs to the focus space that we construct from this omega state. And the question now systematically is that how do we get omega as a function of the state 0? Again, like this is a ridiculous notation, but more or less I'm saying that this omega should be constructed from this free vacuum in a systematic manner. So how do we get there? There are two ways. One way is, this is how Peskin book defines it. And there is also another definition. It's called Gell-Mann law, adiabatic, basically definition of the state. So we can actually talk about both of them and to see if these two pictures are consistent. So we go to the picture 1. So picture 1 is Gell-Mann law theorem. So it's basically an adiabatic evolution of the state. So based on the definition, you can say that how can I really go geometrically from state 0 to state omega? Imagine that try to use your imagination. Imagine if it is this t0, and this t0 is when you turn on the interaction. And imagine at the minus infinity of this t0, I mean very, very far from t0, that you turn on the interaction, you are probably living in a world when the state is 0, or basically the free vacuum of the free Hamiltonian. And in the very other extreme of that, you're living in a space when omega is the vacuum of that particular state. So to go from here to here, you just basically have to go with the evolution operator, u of t and t0, and basically take the limit of that operator. So let's remember how was the form of u and u of t and t0. So this operator was the time-ordered product of the exponential of minus I of t0 to t of hi of t, the integral over dt prime. And this is basically how do we calculate the evolution operator. And now, basically, from what we said, is that the state omega is equal to of u of minus infinity to plus infinity on the state of the free vacuum. But then ultimately you need to normalize it in order to keep the inner product consistent. So you basically have to define anything that you have in the nominator, but also sandwich to the vacuum. So this is the definition of how can we get omega and the state omega from 0. Basically get the state 0 and then evolve it with this particular Hamiltonian, but from minus infinity to plus infinity, and then normalize it to the expectation value of that operator. In this way, you can somehow assure that when you calculate the inner product of the free vacuum to the modified vacuum or state omega, you basically have 1. So with the definition above, we can ensure that the inner product of these two states is equal to 1 based on the definition. It is somehow intuitive to think that they cannot be orthogonal, because if they are orthogonal, it is not really clear that how can you really have a particular free state and then take it with some operator into the state omega. And the whole point is that the definition above is not a unitary evolution. It's not a unitary evolution because u itself is a unitary operator, but then you are dividing it into onto the size or expectation value of this unitary operator. So the whole process itself is not a unitary operation. And basically, with a non-unitary operation, you cannot take one particular state into the orthogonal or into another state which is orthogonal to the initial state. But this is just intuitively suggesting us that the state omega and a state of free vacuum are in parallel. So their inner product is 1, but they are not definitely the same entity, but they can kind of converge to each other by this epsilon parameter. So I mean, the space between these two particular eigenvectors is continuous, or there is a continuous function with epsilon, and when you take this epsilon to 0, you're basically getting your eigenvectors and eigenvalues converging to each other. So they cannot be orthogonal, and again, because orthogonality of these two states are really counterintuitive. They should be the same entity, but slightly deviating from each other, not completely being orthogonal to each other. Okay, and now how can we really practically calculate this integral? This is not really intuitive to say that I want to calculate a time order of the exponential of minus I from minus infinity to plus infinity of hi of t dt prime. So one way is that you can always say u of minus infinity to plus infinity is the limit. This is how you can define it. Is the limit of the same entity, but you define a kind of upper and lower bound for your integral, and then you integrate it over this particular volume, and then you take t to infinity. This is one way. There is another way that we can define, and this is somehow getting related to this gets related to the concept of adiabatic operator. So instead of getting the bound from minus infinity to plus infinity, there is another way. You can define minus infinity as one of the lower bound and 0, and then you define this parameter epsilon here, or basically the infinitesimal adiabatic parameter. And then you can say, I am defining this operator as the time ordered of exponential of minus I from minus infinity to 0. And then you have the same Hamiltonian, same integral, but now you propose a new exponential, and this new exponential is basically minus epsilon to the absolute value of t prime. So that would ensure that this integral is going to be converged. So in the limit of epsilon goes to 0, this integral is going to converge. So we can redefine the state omega as u of epsilon minus infinity to 0 of the state 0, and then divide it into the expectation value of it, and then you take the limit of epsilon to 0. And that is somehow more intuitive to say that I want to take some limit to 0 instead of taking a limit to infinity. And you can probably guess why. Mostly in computational approaches, when you have to calculate an integral in the computational manner, if you expand your boundaries that you take the integral to infinity, that's basically counterintuitive. They need more resources and more calculation. So there are some tricks to basically take this integral and turn it into a kind of regulated integral, but then you take the epsilon to 0. So that's one way. So that's the definition of this particular state. And that somehow conclude that how can we get the, theoretically, how can we get this vacuum state from the free vacuum? So the definition that we presented above is like an intuitive definition of the state omega. So in the systematic way, Peskin in Peskin book, in page I think 86, it is showing us systematically how to calculate the expectation value of the time order of phi x, phi y, or 2-point correlation of the interacting fields over the modified vacuum or over the vacuum of the interacting Hamiltonian. So we want to see how to systematically calculate that without really relying on this intuitive definition of the modified vacuum. So to start with that, I'm going to write down an equation. I'm going to write down a equation here. So the exponential of the total Hamiltonian over some time t evolve the state 0. So imagine this is basically how we start from the state 0 and then evolve the state with the Hamiltonian operator over the time length of t, and then basically t goes to infinity. But here, I want to show you a little bit of mathematical trick. So basically, we can project the state 0 onto the eigenstates or eigenvalues of the total Hamiltonian of interacting Hamiltonian. So basically, a state 0 can be written as the sum over the state 0 over the new basis n that starts from 0 to infinity over the estate of n. Just basically using the completeness of the basis and projected any kind of particular basis into the eigen values of the total Hamiltonian. So to distinguish that, the total Hamiltonian, or I can say that the estate n is when the total Hamiltonian, or H0 plus H interaction, acts on the state n, it gives me E prime of n of n. So these n are constructed, or they belong to the same focus space that we make from the state omega. So you have the state omega, and then you have n1 to np. And basically, these are made out of the a dagger of k acting on the state omega. So I'm going to take this away. So I'm going to have this in the mind. And then I'm going to continue writing down this expression. So this is equal to minus ht of sigma n from 0 projected on those states. And then I'm going to separate the 0 from the rest of the n's. And you know why? Because I want to isolate the omega. So this is equal to minus ht of omega 0 omega plus exponential of minus ht on the state n equal to 1 to infinity of 0, the free vacuum on n. And this can now go into this particular states, because by definition, this or n are the eigenvectors of this Hamiltonian operator here. So this is equal to, the first term is the same. The second term is going to have the sum over the exponential of n equal to 1 to infinity minus I e n prime t n over 0 n. And I want to get rid of this second term, and you know why? Because, again, I want to get this. I want to get this omega. So I need to get rid of all of that. How can I get rid of all of that? I'm going to go to this exponential term. So this is an exponential with a complex number. So to get rid of that, instead of saying t goes to plus infinity, we say t goes to, I know that mathematicians hate to see that. The physicists are just basically taking it to infinity. But instead of taking t to plus infinite of the real time, I'm gonna give some imaginary component to time. And then again, I don't know if you remember about the propagators. When we were calculating these propagators in the free fields, we have this epsilon on the denominator. We wanted basically the denominator not to be 0. And basically, after all, take epsilon to 0 to get now well-defined parameters. So when we introduce this epsilon, or this, we can call it a regulation factor, this regulation factor later is taken out. So we don't have to be worried about the concept of imaginary time, because it is fair to ask whether time has real component and imaginary component at the same time. So there is a concept called Euclidean time. Euclidean time is the rotation of time from real axis to the imaginary axis. But this is not the concept here. I just want to say it's a mathematical trick. Instead of taking t to plus infinity, take it to plus infinity minus some I epsilon. And the reason is because to get rid of this I here. And then we take the epsilon later to 0. So I'm going to have exponential. The first term is this is the first term. The second term is going to be like exponential of minus en t if we absorb that imaginary component epsilon of n 0 to n. Then these terms for the n equal to 1 to 0, for these terms, epsilon, sorry, t goes to infinity over a small shift on the imaginary axis of that. These terms are going to be 0, or they can converge more and more compared to this term, because you have this hierarchy. The hierarchy is like you have E0 prime, and then you have E1 prime, and so on. Let's say any kind of En prime. So there is this hierarchy, and this hierarchy allows you to take out the second term, or the summation of all the other excited states, and just leave with the first term. So imagine that now this is an equation. I turn this equation into approximation of equation. So exponential of minus ht over 0 is approximately going to be, on the limit of t goes to infinity, is approximately going to be exponential of minus ht omega 0 omega. And then again, this can go inside of this, and we're going to have exponential of minus e0 prime t omega 0 omega. And now we don't even have to specifically mention that what this term is going to be. We already defined that omega and 0, based on the definition that we provided above by the Gelman law theorem, omega and 0 are going to have the inner product equals to 1 based on the definition. So they are in parallel. They're similar to each other, but in parallel. But here we don't essentially need to know this term. Imagine that we don't know this term. Imagine that we don't know this term, and we're gonna see how is it gonna be cancelled out. And basically, we don't even know, even if we don't know that the inner product of the state omega and 0 are going to be 1, this expectation value here can be well defined even without knowing that. So what's the trick? So now from this, you can say the state omega is equal to the limit of t goes to infinity minus I epsilon of exponential of minus E0 prime t omega 1. Now it has minus 1 because this is on the other side of minus IH t over 0. So what I just basically did is to multiply the right side into this argument. So the right side factors are going to go away, and we're only going to stay with omega term, and it goes to the left side. So this is the left side, and this is the inverse of right side equation, right side factor. So this is just mathematically, right? I'm just saying mathematically, omega is equal to the limit of t goes to infinity of I minus I epsilon exponential of minus E0 prime t over 0. And this is something that we want because we know what's the free vacuum, and then we know this total Hamiltonian, and then this term is somehow unknown to us. So this definition is not giving us the complete definition of omega. If you compare this omega into this omega, here you don't really have, in this definition, the red one that I'm highlighting, you don't really have any kind of unknown things. You basically know u, and you know how to apply u to 0. But here we have this extra term that we don't know what they are, but they're going to cancel out. But I'm going to use some mathematical tricks to reconstruct the u out of this. So how do we do that? We basically can shift this t into t plus some t0. And the reason that I'm using this t0 is because I'm going to reconstruct u of t0 and t, or u of t0 and minus t. So I want to reconstruct these operators because u is something that I know. And the way to do that is to shift the time into t plus t0. And it doesn't matter because t is going to infinity. So if t goes to infinity, if you shift it into the amount of t0, it's not going to change your total time. So this t0 is very, very small than this t. So this t is basically the time interval of basically from, let's say, this is t0 here. So this is also t. Imagine this t has a lot of distance from this minus infinity. So this t is very larger than t0. So I mean, you're assuming essentially that, even imagine this is your timeline. Your interaction starts very early. So basically at the very everything is squeezed to infinity. But imagine if you start from infinity, your t0, your t0 is going to be near to the end spectrum, and then your t is around here. So basically you can approximate this t is very larger than this t0. But again, the reason that I add this t0 is because I want to reconstruct this u of t0 and minus t, and u of t0 and t. So omega is equal to the limit of time. Now, in the first parentheses, I have exponential of minus E0 prime. I want to use this prime for E0 because it's a modified vacuum. And then instead of t, I would say t plus t0. And then you have omega and 0. And then you have this minus 1 term here. And then you have exponential of minus h of t plus t0 on the state of the free vacuum. And this is going to be equal to the limit of the same entity. Now I'm going to basically change the first parentheses here as exponential of minus E0 prime now I'm going to say, instead of t plus t0, I'm going to say t0 minus t. And as you can probably guess, this is because I want to make I want to do the arithmetic in the way that I would end up in getting the u operators or the evolution operators. Omega 0 minus 1, and then I'm going to have exponential of minus IH t0 minus t, and basically exponential. And now I can break this h into h int plus h0. And the reason I have to do that because h int is what I want for the interaction picture. So for the interaction picture, I'm going to have limit of t goes to, everything is the same, and then here I'm going to have exponential of minus h0 t0 minus t times exponential of minus h int t0 minus t, act on the state 0. Sorry that if we have too much argument. And then I'm, based on the fact that these two can commute, then the state 0 goes to this h0, and that is equal to the limit of u operator of time t0 and minus t act on the vacuum. So this is how I'm going to take this u of t out. So I can basically express the ket version of omega with the similar limit of, this time everything is ket, and you have u of t and t0, and then you're going to have the same expression here. And now you still don't know this inner product. But when you have this omega, now omega act on phi of x and phi of y, you will see that everything is naturally going to cancel out. Very beautiful. So this is equal to the limit of t, limit of time, and then let's rewrite everything from the left to the right. So I'm going to have the exponential of minus e0 prime t minus t0, 0 omega minus 1 state 0 here, and then I have a u of t and t0 times, then I have the u of x0 to the t0 for the evolution of the phi x dagger here. So I have the phi I of x. So that was a free field of x. And then here you have u of x0 to t0, because again, like phi of x is going to be u dagger u of phi I of x, right? Or sorry, maybe you can say u dagger u. So it doesn't really matter because you can always interchange this definition. But so you have u dagger of phi x, and then you have phi of, or you have u of x0 and t0, and then you are followed by u of y0 to t0 dagger, phi of free y, or the free field at point y, and then you have u of y0 to the t0. Now you have to write down the bra of the omega. So the bra of the omega, this is a very long equation, is u of t0 to minus t, 0, and then you have all those exponential terms here, minus epsilon, minus exponential of minus I e0 prime, t0 minus t, and then omega and 0 minus 1. So you ultimately are going to have the limit of t. Now you have two of these entity, so you have 0 and omega. Sorry. You have 0 and omega. So you have the absolute value to the power of 2 because you have two of them. So you have one here and you have one here. And then you're going to have the exponential term of minus I E0 prime 2t, because the t zeros are going to cancel out. Then you have this power of minus 1. And then you have this state 0 u of t to x0 phi I of x, then u of x0 y0, because they have this property that u of t1 t2 u of t2 t3 is going to be u of 1 u of t1 and t3, right? So because we know this property of u, then we basically are going to take out this entity into one entity of x0 to y0. And then you have phi I of y, and then you have another, the last term of u of y0 to minus t over the state of vacuum. Now, if you look at this side, everything is here, is basically known. So you only have the expectation value of the free vacuum that you know how to calculate. Now imagine that I'm going to use a trick because I still don't know this term. The first term is unknown. So the first term is unknown, right? I want to calculate the first step. So to do the first step, I'm going to basically use this term that instead of phi x and phi y, I'm going to replace them by an identity because it doesn't matter. This equation should be still hold. So basically, instead of having omega time order of phi x and phi y, I'm going to replace this with the basically unitary operator, or basically using the same. So I'm going to have omega, and this is equal to 1, but this is equal to now the first term. And then on the second term, we're going to get rid of these phi of I and phi of y of x, and we're basically going to have 0, 0, then u of t to t0. We don't have any phi in between. And then I have u of t0 to minus t based on the definition. And then I'm going to conclude that this weird term here, sorry, the first weird term. So then the first weird term is going to be, so I can say this weird term this is going to be 1 over that. And then we can even more simplify to say 0, 0 from u of minus plus t, sorry, u of the capital T to the u of capital minus t. Now I have this term. That's really good, right? So basically now I can ultimately conclude that this expectation value, which means the 2-point correlation of the interacting field and interacting states, is going to be very simplified. So the first weird term is going to be on the denominator. So 0, 0. This is what we know, u of t to minus t. And then on top, I'm going to have 0 and 0. And then I have u of t to x0 phi I of x. Then I'm going to have u of x0 to y0 phi I of y. And then the last term, sorry, I'm going to extend the last term of u of y0 to minus t. So, and then I take the limit of t goes to infinity. And then I also have to take the epsilon to 0. And this is how we know how to calculate the right-hand side, because everything is now free. So we ultimately reached to the goal of calculating the 2-point correlation of the interacting systems into this whole new expression. So I can basically simplify it into the limit of t and epsilon of, so I'm gonna rewrite the top as phi I phi of y, phi I of y, and then I have the exponential term of minus I from minus t to plus t. So I'm going to express basically that u instead of, I'm going to express that u in terms of exponential of the interacting Hamiltonian of dt hi of t. And so this is basically, and all of these terms, all of these operators should be time ordered. So everything should be time ordered, right? You agree? Because this time ordering is keeping the causality manually alive. And then on the bottom, I'm going to have 0, 0, then exponential of minus I, minus t to plus t, hi of t, dt. And that's it. So we basically know how to calculate the right side numerically, and then we calculate it and take the limit for time and then for epsilon to get to this 2-point correlation. So with this, we conclude the whole argument of how to calculate the expectation value of the interacting field. So the next step is going to be how to calculate endpoint correlation, and then how to use those endpoint correlation to use Feynman diagrams. For the next session, so we're going to talk about Wick's theorem. So now the question is that if I have this state 0, 0, and then instead of having 2 points, I'm going to have so many points. Imagine x1 to xn. Imagine that I'm going to have an n-point correlation function. How can I systematically do that? So there is a theorem, it's called Wick theorem, just using 2x2 commutation and anti-commutation to simplify that version. So Wick theorem is going to be the base tool of calculating Feynman diagrams, but essentially these are going to be the Feynman diagrams. And we will see the Feynman diagrams. We previously talked about Feynman diagrams are propagators and the mixture of propagators. So, the Feynman diagram is when something comes in, something comes out. So you will see that how these Feynman diagrams, or the visual picture of them, are proportional to the integrals that we calculate, the similar integrals that we calculate above. So on the next session, we will learn how to do Feynman diagrams for a very, very basic kind of interacting field, which is phi 4. So imagine this Lagrangian that we talked about is going to be more advanced. But imagine for the scalar field, only for the scalar field, you had this phi dot 2 plus phi 2, and then you have some lambda phi 4. And this is like a kind of self-interaction. And this lambda goes to 0, or this lambda is very small. Maybe I have to write it like that. But this is a very kind of simple interaction picture, and you don't really have two fields, you only have one field. So this field having this kinetic term and this have this potential term, these two terms are free, and then you have this interacting term. And this is something that you call it phi of I, and then this is how you calculate this integral. So I know this session was a little bit complicated, but I hope that if you go to the sources, into the books, you can definitely study these equations and this calculation with much more details, and perhaps we are skipping some of these steps in order to have a reasonable timeline. So, but here in this session, we learn how to calculate this expectation value from for the interaction picture. So we previously talked about how the Hilbert space is spanned by different bases, and we basically want to go from the free bases to the interacting bases, and we talked about all of this evolution, adiabatic evolution, and then ultimately how to systematically calculate this expectation value that we are interested in. So I see you on the next session, and thank you so much for watching this episode.